In the field of mathematical optimization, stochastic programming is a framework for modeling optimization problems that involve uncertainty. Whereas deterministic optimization problems are formulated with known parameters, real-world problems almost invariably include some unknown parameters. When the parameters are known only within certain bounds, one approach to tackling such problems is called robust optimization. Here the goal is to find a solution which is feasible for all such data and optimal in some sense. Stochastic programming models are similar in style but take advantage of the fact that probability distributions governing the data are known or can be estimated. The goal here is to find some policy that is feasible for all the possible data instances and maximizes the expectation of some function of the decisions and the random variables. More generally, such models are formulated, solved analytically or numerically, and analyzed in order to provide useful information to a decision maker. As an example, consider two-stage linear programs. Here the decision maker takes some action in the first stage, after which a random event occurs affecting the outcome of the first stage decision. A recourse decision can then be made in the second stage that compensates for any bad effects that might have been experienced as a result of the first stage decision. The optimal policy from such a model is a single first-stage policy and a collection of recourse decisions defining which second-stage action should be taken in response to each random outcome. Stochastic programming has applications in a broad range of areas ranging from finance to transportation to energy optimization. This article includes an example of optimizing an investment portfolio over time. Two-stage problems. The basic idea of two-stage stochastic programming is that decisions should be based on data available at the time the decisions are made and should not depend on future observations. Two-stage formulation is widely used in stochastic programming. The general formulation of a two-stage stochastic programming problem is given by, where is the optimal value of the second-stage problem? The classical two-stage linear stochastic programming problems can be formulated as, where is the optimal value of the second-stage problem? In such formulation is the first-stage decision variable vector, is the second-stage decision variable vector, and contains the data of the second-stage problem. In this formulation, at the first stage we have to make a here and now decision before the realization of the uncertain data, viewed as a random vector, is known. At the second stage, after a realization of becomes available, we optimize our behavior by solving an appropriate optimization problem. At the first stage we optimize the cost of the first stage decision plus the expected cost of the second stage decision. We can view the second stage problem simply as an optimization problem which describes our supposedly optimal behavior when the uncertain data is revealed, or we can consider its solution as a recourse action where the term compensates for a possible inconsistency of the system and is the cost of this recourse action. The considered two-stage problem is linear because the objective functions and the constraints are linear. Conceptually this is not essential and one can consider more general two-stage stochastic programs. For example, if the first-stage problem is integer, one could add integrality constraints to the first-stage problem so that the feasible set is discrete. Nonlinear objectives and constraints could also be incorporated if needed. Distributional assumption equals. The formulation of the above two-stage problem assumes that the second-stage data can be modeled as a random vector with a known probability distribution. This would be justified in many situations. For example, could be information derived from historical data and the distribution does not significantly change over the considered period of time. In such situations one may reliably estimate the required probability distribution and the optimization on average could be justified by the law of large numbers. Another example is that could be realizations of a simulation model whose outputs are stochastic. The empirical distribution of the sample could be used as an approximation to the true but unknown output distribution. Discretization equals, to solve the two-stage stochastic problem numerically, one often need to assume that the random vector has a finite number of possible realizations, called scenarios, say, with respective probability masses. Then the expectation in the first-stage problem's objective function can be written as the summation, and, moreover, the two-stage problem can be formulated as one large linear programming problem. When has an infinite number of possible realizations, the standard approach is then to represent this distribution by scenarios. This approach raises three questions, namely, how to construct scenarios, see a radian per second Euro scenario construction. How to solve the deterministic equivalent. Optimizers such as CPLEX, GLPK and Gurobi can solve large linear nonlinear problems. An EOS server hosted at the Argonne National Laboratory allows free access to many modern solvers. The structure of a deterministic equivalent is particularly amenable to applied decomposition methods, such as Bender's decomposition or scenario decomposition. How to measure quality of the obtained solution with respect to the true optimum. These questions are not independent. For example, the number of scenarios constructed will affect both the tractability of the deterministic equivalent and the quality of the obtained solutions. Stochastic linear program. A stochastic linear program is a specific instance of the classical two-stage stochastic program. A stochastic LP is built from a collection of multi-period linear programs, each having the same structure but somewhat different data. The two-period LP, representing the scenario, may be regarded as having the following form. The vectors and contain the first period variables, whose values must be chosen immediately. The vector contains all of the variables for subsequent periods. The constraints involve only first period variables and are the same in every scenario. The other constraints involve variables of later periods and differ in some respects from scenario to scenario, reflecting uncertainty about the future. Note that solving the two-period LP is equivalent to assuming the scenario in the second period with no uncertainty. In order to incorporate uncertainties in the second stage, one should assign probabilities to different scenarios and solve the corresponding deterministic equivalent. Deterministic equivalent of a stochastic problem equals, with a finite number of scenarios, two-stage stochastic linear programs can be modeled as large linear programming problems. This formulation is often called the deterministic equivalent linear program, or abbreviated to deterministic equivalent. For example, to form the deterministic equivalent to the above stochastic linear program, we assign a probability to each scenario. Then we can minimize the expected value of the objective, subject to the constraints from all scenarios. We have a different vector of later period variables for each scenario. The first period variables and are the same in every scenario, however, because we must make a decision for the first period before we know which scenario will be realized. As a result, the constraints involving just and need only be specified once, while the remaining constraints must be given separately for each scenario. Scenario construction. In practice, it might be possible to construct scenarios by eliciting experts' opinions on the future. The number of constructed scenarios should be relatively modest so that the obtained deterministic equivalent can be solved with reasonable computational effort. It is often claimed that a solution that is optimal using only a few scenarios provides more adaptable plans than one that assumes a single scenario only. In some cases, such a claim could be verified by a simulation. In theory, some measures of guarantee that an obtained solution solves the original problem with reasonable accuracy. Typically in applications, only the first-stage optimal solution has a practical value, since almost always a true realization of the random data will be different from the set of constructed scenarios. Suppose contains independent random components, each of which has 3 possible realizations, then the total number of scenarios is. Such exponential growth of the number of scenarios makes model development using expert opinion very difficult even for reasonable size. The situation becomes even worse if some random components have continuous distributions. Monte Carlo sampling and sample average approximation method equals, a common approach to reduce the scenario set to a manageable sizes by using Monte Carlo simulation. Suppose the total number of scenarios is very large or even infinite. Suppose further that we can generate a sample of replications of the random vector. Usually the sample is assumed to be independent identically distributed. Given a sample, the expectation function is approximated by the sample average. And consequently the first stage problem is given by This formulation is known as the sample average approximation method. The SAA problem is a function of the considered sample and in that sense is random. For a given sample, the SAA problem is of the same form as a two-stage stochastic linear programming problem with the scenarios, each taken with the same probability. Statistical inference. Consider the following stochastic programming problem. Here is a non-empty closed subset of, is a random vector whose probability distribution is supported on a set, and in the framework of two-stage stochastic programming, is given by the optimal value of the corresponding second-stage problem. Assume that was well-defined and finite-valued for all. This implies that for every the value is finite almost surely. Suppose that we have a sample of realizations of the random vector. This random sample can be viewed as historical data of observations of, or it can be generated by Monte Carlo sampling techniques. Then we can formulate a corresponding sample average approximation. By the law of large numbers we have that, under some regularity conditions converges pointwise with probability 1 to as. Moreover, under mild additional conditions the convergence is uniform. We also have, that is an unbiased estimator of. Therefore it is natural to expect that the optimal value and optimal solutions of the SAA problem converge to their counterparts of the true problem as equals consistency of SAA estimators equals, suppose the feasible set of the SAA problem is fixed, that is, it is independent of the sample. Let n be the optimal value and the set of optimal solutions, respectively, of the true problem and let n be the optimal value and the set of optimal solutions, respectively, of the SAA problem. Let n be a sequence of real-valued functions. The following two properties are equivalent, for any and any sequence converging to it follows that converges to, the function is continuous on and converges to uniformly on any compact subset of. If the objective of the SAA problem converges to the true problem's objective with probability 1, as uniformly on the feasible set, then converges to with probability 1 as. Suppose that there exists a compact set such that, the set of optimal solutions of the true problem is non-empty and is contained in, the function is finite-valued and continuous on, the sequence of functions converges to with probability 1, as, uniformly in, for large enough the set is non-empty and with probability 1. Then and with probability 1 as. Note that denotes the deviation of set from set, defined as. In some situations the feasible set of the SAA problem is estimated, then the corresponding SAA problem takes the form. Where is a subset of depending on the sample and therefore is random. Nevertheless consistency results for SAA estimators can still be derived under some additional assumptions. Suppose that there exists a compact set such that, the set of optimal solutions of the true problem is non-empty and is contained in, the function is finite-valued and continuous on, the sequence of functions converges to with probability 1, as, uniformly in, for large enough the set is non-empty and with probability 1, if and converges with probability 1 to a point, then, for some point there exists a sequence such that with probability 1, then and with probability 1 as equals asymptotics of the SAA optimal value equals, suppose the sample is IID and fix a point. Then the sample average estimator, of, is unbiased and have variance, where is supposed to be finite. Moreover, by the central limit theorem we have that, where denotes convergence in distribution and has a normal distribution with mean and variance, written as. In other words, has asymptotically normal distribution, that is, for large, has approximately normal distribution with mean and variance. This leads to the following % confidence interval for where and is the sample variance estimate of, that is, the error of estimation of is of order. Multistage portfolio optimization. The following is an example from finance of multi-stage stochastic programming. Suppose that at time we have initial capital to invest in assets. Suppose further that we are allowed to rebalance our portfolio at times but without injecting additional cash into it. At each period we make a decision about redistributing the current wealth among the assets. Let be the initial amounts invested in the n assets. We require that each is non-negative and that the balance equation should hold. consider the total returns for each period. This forms a vector-valued random process. At time period, we can rebalance the portfolio by specifying the amount invested in the respective assets. At that time the returns in the first period have been realized, so it is reasonable to use this information in the rebalancing decision. Thus, the second stage decisions, at time, are actually functions of realization of the random vector, that is. Similarly, at time the decision is a function of the available information given by the history of the random process up to time. A sequence of functions, with being constant, defines an implementable policy of the decision process. It is said that such a policy is feasible if it satisfies the model constraints with probability 1, that is, the non-negativity constraints, and the balance of wealth constraints. Where in period the wealth is given by, which depends on the realization of the random process and the decisions up to time. Suppose the objective is to maximize the expected utility of this wealth at the last period, that is, to consider the problem. This is a multistage stochastic programming problem, where stages are numbered from 2. Optimization is performed over all implementable and feasible policies. To complete the problem description, one also needs to define the probability distribution of the random process. This can be done in various ways. For example, one can construct a particular scenario tree defining time evolution of the process. If at every stage the random return of each asset is allowed to have 2 continuations, independent of other assets, then the total number of scenarios is. In order to write dynamic programming equations, consider the above multistage problem backward in time. At the last stage, a realization of the random process is known and has been chosen. Therefore, one needs to solve the following problem. Where denotes the conditional expectation of given. The optimal value of the above problem depends on and is denoted. Similarly, at stages, one should solve the problem whose optimal value is denoted by. Finally, at stage, one solves the problem equals stage-wise independent random process equals, for a general distribution of the process, it may be hard to solve these dynamic programming equations. The situation simplifies dramatically if the process is stage-wise independent, that is independent of 4. In this case, the corresponding conditional expectations become unconditional expectations, and the function does not depend on. That is the optimal value of the problem. And is the optimal value of 4. Stochastic programming for nonlinear optimization. Many of the optimization problems in science and engineering involve nonlinear objective functions with uncertain model. In these cases, stochastic programming is applied to optimize the expected objective over a set of realizations generated using Monte Carlo simulation. For expensive function evaluations, model selection is used to reduce the number of realizations. Techniques such as out-of-sample validation is used to reduce the number of required realizations and the number of representative realizations. Recently, optimization with sample validation is proposed to significantly reduce the computational cost in stochastic programming for expensive function evaluations. Optimization with sample validation determines, in a systematic way, the number of realizations in optimization to adequately represent the entire set. Stochastic programming with OSV has been applied for optimization of oilfield development planning. Biological applications. Stochastic dynamic programming is frequently used to model animal behavior in such fields as behavioral ecology. Empirical tests of models of optimal foraging, life history transitions such as fledging in birds and egg-laying in parasitoid wasps have shown the value of this modeling technique in explaining the evolution of behavioral decision-making. These models are typically many-staged, rather than two-staged. Economic applications. Stochastic dynamic programming is a useful tool in understanding decision-making under uncertainty. The accumulation of capital stock under uncertainty is one example. Often it is used by resource economists to analyze bioeconomic problems where the uncertainty enters in, such as weather, etc. Software tools. Modeling languages. All discrete stochastic programming problems can be represented with any algebraic modeling language, manually implementing explicit or implicit non-anticipativity to make sure the resulting model respects the structure of the information made available at each stage. An instance of an SP problem generated by a general modeling language tends to grow quite large, and its matrix loses the structure that is intrinsic to this class of problems, which could otherwise be exploited at solution time by specific decomposition algorithms. Extensions to modeling languages specifically designed for SP are starting to appear. C. AIMMS supports the definition of SP problems. EMP-SP, a module of GAMS created to facilitate stochastic programming. Func Designer, free software that includes stochastic programming and optimization by OpenOpt solvers. Example 1, Example 2, Example 3, SAMPL, a set of extensions to AMPL specifically designed to express stochastic programs. They both can generate SMPS instance-level format, which conveys in a non-redundant form the structure of the problem to the solver. Solvers equals, FortSP, solver for stochastic programming problems. It accepts SMPS input and implements various decomposition algorithms. NEOS solvers, 3 solvers are available in the NEO server, bouncing nested Benders solvers for multistage stochastic linear programs, DDSIP for 2-stage stochastic programs with integer recourse, and stochastic decomposition for 2-stage stochastic linear programs. CoinOS Stochastic Modeling Interface, an open-source project within CoinOR. It can read stochastic MPS input format as well as supports direct interfaces for scenario input, and generates the deterministic equivalent linear program for solution by CoinOS solvers. See also Probabilistic-based design optimization, SAMPL algebraic modeling language, scenario optimization, stochastic optimization, stochastic control. References. Further reading, John Abergent for a section V. Laveau. Introduction to Stochastic Programming. Springer Verlag, New York, 1997. Call, Peter. Wallace, Stein W. Stochastic Programming. Wiley Interscience Series in Systems and Optimization. Chichester, John Wiley & Sons, Limited pp. XA plus 307. ISBN 0-471-95158-7. Mr. 1315300. GCH. FLUG, Optimization of Stochastic Models. The Interface Between Simulation and Optimization. Kluwer, Dordt, 1996. Andres Prekapa. Stochastic Programming. Kluwer Academic Publishers, Dordt, 1995. Andrzej Ruskinsky and Alexander Shapiro Stochastic Programming. Handbooks in Operations Research and Management Science, Volume 10, Elsevier. Shapiro, Alexander. Dencheva, Darinka. Ruskinsky, Andrzej. Lectures on Stochastic Programming, Modeling and Theory. MPS Siam Series on Optimization 9. Philadelphia, Pennsylvania, Society for Industrial and Applied Mathematics. Mathematical Programming Society PPXVI plus 436. ISBN 978-89871-687-0. Mr. 2562798. Stein W. Wallace and William T. Ziemba Applications of Stochastic Programming. MPS Siam Book Series on Optimization 5, King, Alan J. Wallace, Stein W. Modeling with Stochastic Programming. Springer Series in Operations Research and Financial Engineering. New York, Springer. ISBN 978-0-387-87816-4. External links, Stochastic Programming Community homepage.